Hello, in this video, I want to show you how to analyze a very simple frame, a simple braced frame with a uniformly distributed load on the top beam and a uniformly distributed load applied to one of the columns. I just drafted this simple frame by drawing separate lines. And now I want to start using Karamba 3D to analyze this beam. Now, the first step is to transfer the geometry to Grasshopper. I will set multiple geometries. I will hit enter. Now the geometry is transfer. To make sure that I'm not going to use the geometry, I will right click on the geometry and say internalize data. So then if I even delete this, still I will see the geometry in Grasshopper. Now, the next step is to define this geometry as linear elements in Karamba, a composition of beams and columns. Then I need to define the supports. In this example, I'm going to define one roller here and one hinge support here. So I'm going to copy this support component and I need to define the points. So I will call list item component and connect the list of the points that I have. If I want to see what are the points that I have within this frame, I will connect it to a panel. So I want to define a hinge at 0, 0, 0. So the index item for this point here is 0. You see, 0, 0, 0, the index number is 0. So I will connect it to this and say I want to place this support at this point. And then I don't want to allow any translational movement. Now for rotation, this beam, if there is a hinge here, may be able to rotate about axis Y. So I would release Y, but I will restrict rotational movement about x-axis and y-axis. So this is the support. And then again, I call list item, connect the list of the points that I have. And then I want to have another point, another support, a roller support here, which is actually the dimension of this frame is 9 feet by 15 feet. And I'm going to define it as 15, 0, 0. So index 3. Right? This is index 3. So I will connect it here. And then for a roller, I want to allow translational movement along X, but not Y and Z. So I will restrict Y and Z. And rotation again about axis Y. So I will release RY, but restrict rotation about axis X and Z. So these are the supports. One thing that is important at the beginning, I set my Rhino units to feet, but also you need to check and make sure that your Karamba units are also in English units. If it is not, you can go to Karamba 3D physical units and pick the imperial units here if it is on metric, and vice versa. If you want to work with metric systems, you can switch. Now, to assemble the model, I will call assemble model component. Then I will connect the elements to elements and supports to the support input. And since I want to connect two supports, I will hold shift. Oh, I missed it. And connect it to two supports. Now I have two supports. And in order to see what I'm modeling, I will just drop a model view prior to analysis. So I will connect model to model. Now you see there's one support here and one support here, and then I have these four elements. So far we're good. Now, the next step is to define the beam loads. And just to be a little bit more organized, I will just like click the supports and the list items and right click on this canvas and group them. So now I can move them together. And then to define the loads, I will drop two beam loads component. And I want to have two sets of uniformly distributed load, one applied to this top beam and one to this side column. Okay, now first of all, I should define the beam. Here I have a list of elements. I want to see which one it is that I want to apply to. So when I read from the panel, I want to pick this beam. This beam starts from 0, x is 0, y is 0, and z is 9. So 0, 0, 9. It seems this is it. 0, 0, 9. And then the end point is 15, 0, 9. So 15, 0, 9. So the index here is 1. Okay. Now again, I will call list item, connect the list of the elements that I have, and pick index 1. Depending on the way that you drafted your frame, this list might be different. I mean, the index of the beams might be different. So you should always check the coordinates of the beam that you want to connect. Okay, so this is the beam. And the load case, I will call it F1. F1. I will give it a name. And then it will ask for the force vector. I want it to be a downward gravity load acting on that beam. So I will look for a z unit to define the direction. And then I should give it a factor. So I want to consider a 5 kilopounds per linear foot. And then I drop the panel, put a -5, and that -5 will be -5 kilopounds per linear foot. And then I will connect this load to this assembly. You'll see, I see the downward. And here in this case, the orientation is local to the element. which is fine. But like even I switched to global is the same. But I mean, it's a good general practice to consider the orientation always as global because we always want the gravity load be along the negative direction of the z-axis. And then here, the T position defines the start and the end point of the beam, and it should be a number between 0 to 1. If we do not define a beginning and end point, by default, it will be throughout the length of the beam. So this will be 0, this will be 1, and I will keep them as is, as they are, okay? So that should be fine. And then for the next load, again, I call this item, and then I will connect it to the beam. And I will connect the list of the elements that I have to this list item. And now I want to apply the next load to this column. So this starts from 0, 0, 0 to x is 0, y is 0, and z is 9. So I should look for such element. So here, 0, 0, 0 to 0, 0, 9. So index 0 will be the next element. Okay, there we go. And then the load case is F2. F2. And then the force should be along the X direction. I want to apply it toward the right direction of the X. So I will this time look for unit X. Okay. And I will give it a factor. I wanted to have a 2 kilopound per linear foot. And since I want it to be toward the right direction of X, it can be positive. And I wanted to get applied all throughout the length of the column. So I will keep T0 and T1 by their default values. And then I will also connect the loads to this load assembly. And then I will right click on the loads, flatten them. Here again, I'm not seeing F2 because I only have 2 load cases. So that is F1 and this is F2. So this here, now you can see the difference between the load being local to the element or be global. So if I change it to global, then the X will be toward the direction of the global XYZ Cartesian coordinate system. So make sure that this is a global orientation. Now I don't have any other item here to show the combination of the loads. So I need to add that. Under load, I should say load case combinator. And what is that? So load case combination rule. I will just drop a panel, say FT equals F1, F1 plus F2. Here you should be careful if you insert the name of load cases with uppercase letters. Here they should be exactly the same. They should exactly follow the same order. All right, now again, I connect that load case combinator to the load. And here now I have FT. Okay. And wait a second. There is another component, load case combination setting. In order to be able to see that, I will just again drop if T as the name, lowercase, and connect this to the load cases. Okay, you can connect that or don't do that. As long as you don't want to use any initial element definition and like change the type of the calculation. It doesn't matter if you add this one or not. You can even like forget about it. And now you have both loads. Then the next step is to analyze the beam. So you're going to say, here are the models, analyze models, and here is where the magic happens, and then connect the analyze model to this model. And um, I'm not seeing anything here. That's because, although there is FT here, because I just misconnected that. So lowercase combination. This should be, oops, this lowercase combination should get connected. Holding the shift before analyzing. Okay, so this is F1, F2, F total. So we see both loads. Then I will connect the analyze model to the model view. Ooh, crazy. That shows all the displacements. I will just reduce the scale. You see? Scale of graphics showing the displacement. You can actually read the displacement value here in inches. So there will be like 13 inches. Oh, that's huge. And then, well, that seems that that's too much, but it doesn't matter for now. And the next thing we want to see is the axial loads in this frame. So I will also connect the analyzed model to the beam view here. And okay, under the section forces, you can look at the NX, which shows the axial loads in the members. Okay, these lines doesn't make any sense to you. I will say why, because it is just drawing a diagram. I will just turn off the model view so then you can better see the beam view. And then also here, in addition to NX, I will say fill, and I will change, I will reduce the scale of the loads in kips. And I will say, okay, show the numbers. Now I can better see the numbers. All right. So here, it's a little bit tricky to read the numbers, but it doesn't matter. Here, it seems that these are the numbers. And as you see in this diagram, the amount of axial force in each member is kind of shown by a chart, a diagram. And the magnitude of those loads are represented in terms of these areas and these lengths, and the values are given here. So to read that, this 2.49 is the amount of load in this little axial element, this bracing element. The axial load in this bracing element is 2.4. Then for this bottom horizontal element, it's 6.25, the number close to this line. And for this column, it is 36.54. That 36.54 kilopounds basically is showing the diagram representing the magnitude of the force in this vertical element. And for this one, the top one, there's a minus 10 kilopounds axial force. And then for this thing, for this column, then the axial force will be minus 37.04. So the magnitude of the forces, the axial forces are given. But what do these positive and negative values mean? For the blue colors or the positive values, that means the force is a kind of tension force. So the element is under tension. And the negative values, like minus 36.54 or minus 10 or minus 37.04, these represent compression elements and the compression forces, and the compression forces are also demonstrated in this kind of like orange reddish color. So that's how you get the force diagram. And this is also on the front view, it's a good representation of the forces. You can play around with a scale sometimes to better read the numbers. And under the display, you can pick cross-section to show the cross-section of the beam, or you will later learn how to play around with other display parameters, learning about the stress in the elements, but this is not the scope of this exercise in this video. I will just turn this off. I just want to see a pure diagram of the and the axial forces. Later, we will learn about shear forces in the beam and like the moment diagram, but now we don't care. We just want to see the neutral and X. We want to see the axial force along the neutral axis of those elements. Okay, that's it.